it should be good. Okay? And laser pointer. Okay, we're good. So thanks again to Roberto. Okay, so what I'm going to be talking about is a project that was started during my former PhD student Zorawar Wadia Singh's PhD thesis. He's now a postdoc. Together with Pete Gonthier and Alice Harding, we've moved it along, and we're almost at the conclusion of a stage, which we're going to submit a paper in the next couple of months. We're just polishing now. So these are the results from that paper. It's modeling quiescent emission of hard X-ray tails, discovered 13 years ago in Magnetars. Okay, so we now all know what Magnetars are. Lots of good talks today, summarizing their general properties. Here they are on the PP dot diagram up here in the red squares with magnetic fields typically above 10 to the 13 Gauss, ranging up to 10 to the 15 Gauss. Okay, so hard X-ray tails, Magnetars were known in quiescent emission in the thermal X-rays, and then we were able to, with Chandra and XMM, see steep X-ray tails to them, and then the discovery led by Wim Hansen and Lucian Kuiper and Peter Den Hartog later, and others have been found these hard X-ray tails in a total now of 9 Magnetars. So they're very, very flat in the new representation. Here is the energy. They extend above 10 kV all the way up to about 150 kV. Then we don't have sensitive actual detections, but we do have upper limits from Compton. And so that's years ago. These were discovered in RXTE data and integral data, and we know now that there must be some turnover here. We don't know what produces it, but it has to be there, and eventually we'll be getting to modeling that. Right now we need added sensitivity in this band in order to be able to really do good spectroscopy. What we also see is that the pulse profiles vary as you go through energy band. If you go from low energies all the way to high energies up here in the RXTE, you find that you get a very much different profile, much broader and less structured profile than you do down in the thermal X-rays from the surface. Okay, here's another blow up. Same thing. Here we are for RxJ 1708, thermal, power law, steep power law tail, RCS type emission, and then we have these very flat spectra, typically e to the -1, that must turn over. Okay, they're common. There are 7 of them where we have detections from Enoto et al. Teru's paper. The thermal, if you look at that in this new representation, same deal, you find that lots and lots of the power in X-rays appears in the hard X-ray tail. So it's non-thermal emission. If you compare it with the Crab pulsar, with Vela up here, and 1509 coming down here, you find that the spectra do this. So they're very, very flat, but they don't extend. And so they are very different from highly magnetized pulsars. Here's some of the data on the actual spectral indices for the 9. And the hard spectrum is typically somewhere between a 1.7 index, 1.1, 1.3, 3, 0.7, 0.93, 0.8. So you can see there's a range of the spectral indices. Those are in the unpulsed spectral indices, which is mostly what we measure. So the idea that came out a few years after the discovery of the tails was that resonant Compton upscattering was a way to get this. Okay? It's a hard thing to avoid, actually, because the systems, while they're optically thin, as long as you have energetic particles around, it's very, very efficient because it's resonant to the cyclotron frequency, the actual scattering cross-section. I'll show you that shortly. So a number of groups have been involved in this. And so what you do is you use hard X-ray, you get the non-thermal hard X-rays purely by a magnetic inverse Compton scattering of the surface thermal X-rays. You've got a big bath of thermal surface X-rays, and you get, just as long as you have relativistic electrons lying around and they're energized by some activation mechanism, they will be heated by inverse Compton scattering up to very hard X-rays and into gamma rays as well. So you could do this by a conventional pulsar electrodynamic potential type model, but that's not actually the preferred model. It's really the large-scale currents associated with twists in the magnetic field, with magnetars associated with the closed field line regions or maybe neighboring boundary quasi-open field line regions. But let's think about the closed field line regions in the equatorial regions. The currents and charge densities along these field lines have to be far in excess of the Goldreich-Julian values. That just comes about because you're talking about 10 to the 35 ergs per second in hard X-ray tail luminosity. So the Putative local scattering is 1 to 10 stellar radii from the surface, above the surface. Okay, physics, resonant Thomson cross-section. So if you're looking at Thomson scattering as we know it from electrodynamics, we have a flat cross-section, just like that, as a function of energy log scale in units of the cyclotron frequency. Okay? At the cyclotron frequency, classical electrodynamics, as evinced in the paper by Canuto and al., shows that you have a resonance that comes directly out of the dispersion and the fact that electrons in a magnetic field get stirred up by an incoming photon. And they get the resonance, and both the modes, the polarization modes that Roberto Girola talked about, are highly resonant here, and they have roughly the same cross-section, but not exactly. They do if both the photons are propagating along the magnetic field, and the preferred state of propagation is circular polarization. However, there's this wide disparity between modes if you're in the low frequency regime, and that's what's been discussed in a couple of talks so far this afternoon. Okay? What we are looking at in this situation is we're actually looking at where the two photons are propagating parallel to the magnetic field, which means theta equals 0, and therefore the cross-sections are essentially identical. And they're resonant here. We have to cap those resonances. You can't, in a classical sense, you don't cap them. It's divergent. So you have to introduce something that's a little bit exceptional, which is quantum mechanics. And in fact, to get it right in strong fields, you actually have to introduce quantum mechanics too, because for this particular problem, we're dealing with ultra-relativistic electrons and photons coming up. So the photons now have a finite energy. They're not very low in the rest frame of the electron. They're actually quite significant. So the cross-section without a magnetic field would be this green line, which is the familiar Klein-Nishina cross-section. It's diving off. This is for a field in units of the quantum critical field, 4 times 10 to the 13 Gauss, and that's 0.1. So that's 4 times 10 to the 12 Gauss. As you increase and get to magnetar fields, you find that not only do you get Klein-Nishina reductions, denoted by, if you like, these purple dots or the black curve, you still get the resonance, but the resonance drops relative to the Thomson value of the cross-section. And you get distortions to the shape, and you have to cap the resonance with the finite lifetime of the intermediate state of the electron. So that's the physics. We put this all into our calculations to get the spectra that I'm going to show you. Okay. There is an element to this we did first, and that was what happens to the particles. That's the cooling. And right now, you have to do the cooling, you have to do the spectral production, which is what I'm talking about today, and then you have to put the two together. We're yet to put the two together. So we did the cooling a few years back, and what you've got is, so you've got these X-rays coming off, and at some interaction point for your upscattering, you have a cone of soft X-rays. It's collimated, it's highly collimated, and it's about the radial direction. Okay, but the magnetic field direction is inclined to that, so the ability to sample kinematics that might set up a resonant interaction, and that resonance is at the cyclotron frequency in the electron rest frame, that depends on where you are on a given magnetic field loop. Low altitudes, you have a high magnetic field. High altitudes, you have a low magnetic field. So if you just take the surface emission, we plotted these general plots of a cooling rate, which is the resonant Compton scattering cooling rate, gamma dot, to the electron Lorentz factor in units of seconds to the minus 1. And a dynamical crossing time at the surface is C over the neutron star radius, so 1 over T escape, if you like, is that line there. It's 10 to the 4 to seconds to the minus 1. And all the curves that you get for different field strengths, 10 to the 2 times B critical, 10, B critical, 0.1, etc., they all have this type of behavior, this morphology. In this regime, it's non-resonant. You're not actually ever accessing the resonance because the Lorentz factor is too low. In this regime, you're getting an inverse image of the Planck spectrum of the surface thermal photons. And that's sort of reversed by the kinematics of the resonant Compton scattering interaction. And then you eventually get into a power law tail. So if you inject particles at low altitudes where they sample high magnetic fields, if they have a Lorentz factor of, say, 10 to the 5, they may hit, for B equals 10 at the surface, they hit this resonance orders of magnitude in cooling rate above the dynamical scale. So they cool rapidly. They go boom like this down to a field that's lower. They continue to cool because the field is still sufficient in order to be able to access the resonant cooling. Then eventually you get to the maximum altitude, the magnetic field stops, and then the particles go around to higher field strengths, but they're now below the resonance, so they're non-resonant. So they don't actually cool, so they stop. That's really what's going to happen. Okay, so now let's look at the spectral production. We're not going to do the actual cooling. What we're doing is developing templates for spectra that you produce and seeing what the general character and how it relates to the neutron star geometry, the magnetar geometry. So here we have a plot of resonant interaction geometry, okay? Maybe I'll focus on this one here because it's closer to this legend. Okay, so here's your neutron star, and your magnetic field's are little faint loops here. It's a little hard to see, but they're your magnetic field loops. And we've just got linear scales in 2 dimensions. With this plane is going to contain the plane of the direction of the line of sight to an observer. So if you'd like to tip the plane around like this, the line of sight to you, the observer. That's how we're viewing it. The viewing angle, the observer is this little eye here. So that's you looking down to the neutron star, and we've got all the magnetic field lines in that plane, and then we've got these contours. These contours are contours of the final upscattered photon energy as a function of position, okay? So what happens is you want to have a resonant interaction, which depends on the initial photon energy, and which is a soft thermal surface X-ray, and the angle of that photon as it comes off the surface makes with the local magnetic field wherever it interacts and scatters. But also, your final photon energy depends on being close to the resonance as well. So there is a direct correlation between final photon energy, which is color-coded from about 10 to the 3 in units of MEC squared down to 10 to the minus 4 in units of MEC squared. So this is gamma rays, this is around the thermal energies, and this is down in UV. These curves, you have pairs of them. One of them sits here, say here's one for 1.6 keV. Here's another one for 1.6 keV. And they're separated, they're pairs. These are curves that indicate resonant interaction locales that produce an energy of 1.6 keV. As you go up in energy, the positions of the resonant interactions converge, and they coalesce eventually near this blue line here. And this blue line here is where you're getting all your gamma rays. But otherwise, you're getting 16 keV. The black line is 160 keV. And so most of your X-ray emission that you would get from this model would appear in these regions here, would come from these regions, okay? But they produce, when you look at it, like you look at the radial, you look at the normal to these curves, these contours, it's not necessarily directed. It's directed up this way. It's not directed towards an observer. So the observer doesn't necessarily see that. Some observer would, but you as an observer would not necessarily see that. So what happens is, if you look at 3-dimensional orthographic projections, you pick a particular viewing angle, which is a function of pulse phase. So if you've got a viewing angle, let's say here, let's say 30 degrees, and that will depend on your phase because that's an instantaneous viewing angle with respect to the magnetic field axis, but the magnetic field is spinning, tracing a cone in space. So you will actually cycle through a sequence of these back and forth as you go through pulse phase. And what you see is it's color-coded with the same color coding, and you see this is the magnetosphere that you see at a particular energy. And what you see is that the black and blue stuff, which is the hard X-rays that are beyond 160 keV and into gamma rays, comes from a very small portion of the magnetosphere. Mostly what you see is red and yellow, and that's soft stuff. That is stuff that is below 150 keV, even well below that, below 10 keV typically. And that is dwarfed by the surface thermal emission. So the magnetosphere is largely producing soft emission. Okay, so now we get to the spectroscopy. Okay, so let's focus on the left first. What we've plotted here is a differential distribution, a straight differential distribution. It's not multiplied by E squared. Here's the energy, here's an MEV up here, and here's a KeV down here. Okay, so the spectra have this really weird sort of stuff going on. They have 2 spikes, a quasi-power in between, and rapid drops here. So you think you've got a resonant cross-section that is entirely resonant, and then you're shifting it left and right in frequency space. Okay? How you shift it depends on the kinematics. The kinematics have 2 elements to it. One is the incoming photon, which is a soft energy, a soft photon of energy in X-rays, which means this is about 10 to the minus, these are scaled in terms of MEC squared, so it's about 10 to the minus 3. It also depends on the angle of the photon with the soft X-ray with respect to the local magnetic field at the point it has a resonant interaction. Okay, so that's one ingredient, and that determines those previous geometric curves that I've talked about. That has to be approximately equal to the B in dimensionless units. But also, in order to, you have your final photon angle and final photon energy, and they're correlated. So if you change your angle with respect to the local magnetic field, which is your viewing angle, your observer viewing angle, instantaneous as a function of pulse phase, then your final photon energy is also couples to this directly. So you see the spectrum changing, since your instantaneous viewing angle is a function of pulse phase, you expect your final photon energy is also strongly a function of pulse phase. What's plotted here are two cases where you look at the spectra, you get the power laws. This power law is roughly e to the plus 1/3. Okay, that's very flat. It's taken for a case where we're not actually looking down a magnetic field plane, but we're inclined by 5 degrees to it. Okay? Here we're orthogonal to it. So instead of the magnetic field plane being like this for you, it's like this. So it's 90 degrees. What you see is when it's like this, the kinematics inhibits Doppler boosting. When it's 5 degrees, you get a fair amount of Doppler boosting, which pushes the spectrum up above 1 MeV. If you take 0 degrees, I'm not going to show that, it comes up here. You get very strong Doppler boosting. Classic kinematics associated with inverse Compton scattering. You back off it a bit, and what you find is, so you get these flat spectra with the cusps, and the cusps are images of the resonant Compton cross-section, the full Compton cross-section. I've also shown data here. Okay? These are all done for different Lorentz factors. Low Lorentz factor, 10, 30, 100, 200, 300. And you sort of see that there are some resonant regimes and there are also non-resonant regimes sitting there. It's all very complicated. And we want, in general, you're going to get a superposition of this type character. If you go to this orthogonal case, your kinematics for your final photons are very different because this angle looks fairly close to 0, so this term tends to disappear. And what it does is it tends to reverse, that you find the hardest spectra come from the lowest Lorentz factor electrons, which basically means the electrons are moving somewhat away from you and you're seeing backscattered photons. Okay? It contrasts the 0 degree case that I'm not going to show, where all these line up in a sequence of the highest Lorentz factor gives you the hardest spectrum. Okay, so some convolution of all this sort of character will appear in the overall spectrum. Okay, we're going to show you one convolution in a couple of slides. Let's first highlight, okay, so now here's another case. Here we're doing now, instead of a variation with Lorentz factor, we're doing a variation with viewing angle. It's instantaneous viewing angle. So as a function of pulse phase, we oscillate sinusoidally between values of these. Okay, so sometimes you're very close to the magnetic pole, sometimes you're very, 180 degrees away in phase, pulse phase, you're well away from it. And you see that you get flat spectra, sort of flat spectra, really flat spectra, but now you get this large suppression of the actual flux. There's 5, 3, 1. So you've got about 4 orders of magnitude in flux. Okay? A little bit of a change in the maximum photon energy. So you sort of see it, you're going to see the spectrum are going to flap around if they're allowed to be just inverse Compton scattering. Okay? However, they're not going to be. Because we're right down close to the surface, we're at 4 times R max represents the maximum altitude of the field loop in units of the neutron star radius, so it's 4. So that's not very high. The magnetic field is always, it's 100 here. The polar magnetic field is 100, so it's 4, that's 50 divided by 4 cubed is what that field is. So it's just about below 1. In other words, the critical field at the maximum extent. Here we show some data from 4U0142, the anomalous X-ray pulsar, in showing its spectrum and its turnover and its upper limits with the Compton upper limits, and you see that these models do not, as they are, from single field loops, do not match that. Okay? You see large drops, resonant regimes, spikes, then non-resonant interactions, strongly resonant interactions, and all of this stuff up here will get reprocessed because we're very close to the surface. Okay? Above 1 MeV, thank you. It will be reprocessed by, actually by pair creation. Okay? Below 1 MeV, photon splitting can take out the extraordinary mode down to even about 50 keV. That's a project that my new graduate student, Kun Hu, is working on. And it's early days yet, but we'll get some results on that fairly soon. And we'll be able to see what the attenuation probabilities are here. And so these photons will get reprocessed. And that's got to be included in the full model, which has to be modeled by a magnetospheric cascade. Okay? Now, variability. So, okay, so if you take those, the right-hand portion of those peaks, sorry, wrong way. Okay. We have just lost our, okay, there we go, it's sensitive. Okay, if we take the right portion of the peaks here and say, this is our maximum energy from the resonant range. Okay, we take that energy, And we say, okay, let's plot it as a function of pulse phase. So now we're taking our theta viewing angle, theta v, is now varying as a function of pulse phase, which is shown here on the x-axis. And we're taking a log of the photon energy there. Here it's 0, it's 0.51, so that's 5 MeV. That is 511 keV down here, so 1 MeV is about here. And we have these curves that are oscillating. Let's take this case where we've got the inclination angle between the magnetic field axis and the rotation axis is 60 degrees, the so-called alpha angle. And you see these large oscillations here, and these oscillations are labeled by different values of a parameter which amounts to different values of the observer's viewing angle zeta in pulsar speed. In other words, the angle between the observer's viewing direction and the actual rotation axis. And you see these large changes. In the upper portion, we've got light contours here because this actually doesn't correspond to resonant emission. It corresponds to non-resonant emission or low resonant emission, deep in sampling deep into the Planck, the exponential tail of the surface thermal Planck spectrum. So this is not very luminous, so you're really only going to detect this type of stuff. Pair creation and photon splitting is also going to get rid of these photons, of these energies, so you're going to see some sort of profile that will do that. The profile depends on alpha, whether it's 30, 60, or 90. You can see vast changes, vastly different changes. So we have the possibility that with this type of study, we'll be able to measure the inclination angle. And if we can measure the inclination angle, we can actually retrofit what is out. We measure the dipole moment times the sine alpha when we do spin down, so we can actually measure the magnetic field better. Okay. Spectra are polarized. That speaks to the sorts of information, the stuff that both Robertos were talking about. When we integrate over a whole bunch of field lines, let's pick a field line and say we have one value of the maximum radius. Then we take all the azimuthal angles as we add up around a sphere, so around the magnetosphere. So what we've got is a toroidal field surface. Okay? If we integrate over that, the stuff where the magnetic field plane cuts the line of sight to the observer, it gives you the hardest emission. Everywhere else is softer. When you add that up, you generally get, by and large, with the exception of when you're looking down the magnetic pole, you get these spectra that are steepened somewhat. Okay, they're steepened, now they're now flat. Okay, so they're now e to the 0. Still doesn't match the data. We've worked at this of how to add up over this. It's not easy to do, to add up over a bunch of different toroidal field surfaces with different R maxes. And we find that the low R maxes give you the hardest emission, but they tend to be fairly low and up at the highest energies, and the small R maxes, the high R maxes at high altitudes tend to give you soft emission, but a large amplitude. And so it tends to give you a spectrum that is not too far from the actual reality of the data. But we're not generating that with any, we're waiting to put the cooling in before we actually really explore that in great detail, because the results will depend on self-consistent inclusion of the resonant cooling as the particles go around the field loop. But it's an encouraging sign, okay, that we will actually step into the form. We will need photon splitting and pair creation to get rid of these photons in order to be able to accommodate the Compton upper limits. Again, these plots are for different viewing angles, instantaneous viewing angles. Okay, so to wrap up, we've sort of got a very good suite now of what we believe are robust spectral templates for what is produced for resonant Compton upscattering, inverse Compton scattering in strong magnetic fields to model magnetar hard X-ray tails. They are strongly dependent on the observer perspective, on the electron Lorentz factor, and on the emission locale. And what you get depends on how you add them up. A lot of the phase space, we can actually meet the Compton upper bounds, but a lot of the phase space, we can't. Okay? Particularly if we actually sample the field lines that are in the plane pointing towards an observer. And we don't really know what the activation is. It's not going to be uniform. It's not going to be a uniform distribution of field line foot point colatitudes or field line foot point azimuths. So we really think that we're going to need pair creation and photon splitting to get rid of the gamma rays and the hardest X-rays. Next step is to actually put the cooling that we've done together with the Compton upscattering spectral studies together. And the best way to do that, I think, is with a Monte Carlo simulation. And we have a lot of those elements actually in place through other projects that we've worked on over the years. We can also do, to a considerable extent, we can actually test it, do code validation with kinetic equations. The output, what we want to do is phase result spectra with polarizations, because the process is naturally polarization. Then it can be folded into the stuff that both Robertos are talking about in terms of the vacuum birefringence, propagate to infinity to see the observer. So in terms of agendas, where we want to set the scene for future Compton polarimeters. Okay, so this is now not IXP or Excite, but actually at the higher energy band above 10 keV. Systems like POET or eAstrogam, where you the sensitivity to be able to probe the tail pulse profile at different energies above, say, around 30 keV, and then we can probe magnetospheric physics and geometry. Thank you.
Thank you, Matthew. There is time for a couple of questions. Lee, please.
Matthew, what happens for higher multiple surface fields?
Okay, everything we've done is for dipole. Okay, so all the kinematics, the kinematical information would be treated on the same footing. The geometry would be different. Okay, so what we want to do is, for example, if we were to say, let's take a toroidal component, the simplest thing, say, put a magnetic field that's a toroid instead of a dipole. Okay, that's the simplest generalization to sort of test this. Okay, that changes the plane of all your information by 90 degrees. Okay, so that means the polarization signals will change. They'll be the same magnitude, but they will change. The field will go up in amplitude, so you will push more towards the higher field result, which tend to be harder. Your viewing point will be, hey, if I'm like, instead of saying I'm along a magnetic dipole axis gives me the greatest Doppler boosting, it will be equatorial planes will pick up the greater Doppler boosting. Okay, so that you can sort of see you get a melange, a mixture of information if you put the two together. And what you get will depend on how you do that complicated geometry when you do field line twists or even multipole moments. And so there's no clear answer to it. We have a sort of a general idea of what we might get, but there's no, it depends on what you put in.
Other questions, comments? May I ask a question? Mm-hmm. Did you actually consider to put in a particle velocity distribution? Or this was just for constant gamma?
These were, yeah, I neglected to say these are monoenergetic, okay? The reason we could do that, what it does is it smears out the results, okay? So you can have a convolution. The point, you can put that in, but that's the whole point of doing the self-consistent cooling, because that generates, instead of just putting in some distribution, you're actually generating the correct distribution for whatever your magnetic field geometry is. And that's best done with a Monte Carlo. So that is our next step.
Okay. Thanks, Matthew, again. And
Thank you.